before you start dishing out drugs to people or using a procedure with people, you collect evidence about it. When I put it that way, it sounds just like common sense. And before, okay, it wasn't not common sense, but it was not as systematic, okay? So for many, many years, the health services have used evidence-based practice. Now, education uses it as well. Here in Scotland, there is a huge movement by Education Scotland to introduce evidence-based practice by taking measurements and by actually looking at what methods work and what don't. Many of you will have come in through a system where evidence-based practice is being used. Okay, so there's lots of things that can be looked at and can be questioned about it. Is it good? Is it bad? Okay, and you need, not only do you need to know if you're going to work in the area of UX or design interfaces, you need to know how to use it. You need to know also how to question it. Because probably I would, well, I've already said this in public, that the most useful method that a manager in a company can have is how to critically evaluate usability data that is presented to them, saying this should now go out to market, this should not, or whatever. Because I'm afraid that the practice can be very uneven. Okay. One of my favorite people in life is a guy called Richard Feynman. Some of you may have heard of him, some of you may not, but you should hear of him. He's dead now, but that's not what he's famous for. He is a Nobel Prize winner in physics, okay? And he's the father of modern quantum mechanics, okay, and quantum theory. And he's probably one of the most interesting lecturers ever. And he did this during a period when there was lots of filming taking place. So you'll find Richard Feynman on computation, for example, on YouTube. And the guy is just fun to actually watch and listen to. Not to mention the fact that he was no slouch. Those of you may remember the Challenger disaster, where the space shuttle blew up, okay? It was Richard Feynman who actually solved the problem. He actually found the O-ring that had ruptured and caused the leak that resulted in an explosion. And again, there's a very famous film of him sitting in a committee. He's easily spottable because all the committee are sacked. But at the same time, he loved to slag off computing science. For example, here's another quote from him from '96. Computer science is not actually a science. It does not study natural objects like physics does, you see. Neither is it mathematics. Rather, computer science is like engineering. It's all about getting something to do something. Okay? You can imagine that this caused much uproar amongst the computer science community. Having said that, he also spent the last 5 years of his life working with his son on designing a quantum computer. Okay, so he wasn't exactly not contributing positively to computing. So, what we're interested in is design. Okay, now the word design is an interesting one because what it does is that it means to make something concrete. Okay. So you're all familiar with this, and by now you've got some idea what you want to do. It's doing the swirly bits in your head, and you want to turn it into something concrete. And in this case, concrete can be as concrete as concrete. Okay, you might be want to building a house. Okay, or it could be a drawing. It's just an idea that is made into something more tangible. Okay, but the word design also means to desire something. You want something. Okay, and I think that that captures pretty much user-centered design, because what you're desiring is something that is usable and has a high UX. Okay, so in the case of user-centered design, the word design means to convert findings of a user requirement study into a concrete proposal for the design of a system. Okay, and so it actually, can directly relate to something concrete. Okay. But this, of course, is the system the users desire. This is what they really want. So both definitions apply pretty well here. When it comes to our system, so in the case of user-centered design, the word design means to convert findings of a user requirement study into a concrete proposal for the design of a system, okay? And so it actually, you know, can directly relate to something concrete, okay? But this, of course, is the system the users desire. This is what they really want. So both definitions apply pretty well here. When it comes to user-centered design, you can sort of summarize it visually in these little diagrams. On the right, you've got what you could call seamless interaction, okay? You've got the machine, you've got the user, and what lies in between is tasks. That is what they're doing. That's what's happening. And it is absolutely natural. Whereas what really happens is in the left-hand top diagram, what you have is human information processing limitations, okay? This is our characteristics, and wonderful as we are, then we still have some characteristics which we cannot really do anything about. I mean, you cannot take a pill and thereby increase your memory by so many gigabytes, sadly, you know. And if you see some adverts for cognitive enhancement vitamins, well, bullshit, okay? It doesn't work. So we're stuck with the way we are. We can train, we can become better, we're wonderful learning machines, okay, but we're more or less stuck with what we do. But what we bring to an interaction is mental models. Now notice how mental models here is actually a sort of cloud-like shape. And that's because a mental model is never actually totally logical or whatever. It is the way we think about a system, the way we understand it. When you're explaining something very complex to someone to do with what you're doing with a computer, you often resort to, well, then there's a few doodads here, isn't it? And it goes up a bit, and you know, I know what happened. You understand it, but explaining it is hard. So you can see how systems ended up with things like the waste bin. Okay? Is there any need to explain to a user that to delete a file is really nothing to do with deletion? It is actually to do with removing a particular label of a bit of data so that it's no longer identifiable as such, but is available, the space, to the system for usage. Do you think that would be useful to your average user? No. So the metaphor is very simple. You bin it, okay? But that doesn't mean that inside the computer that there are some bin men who come and collect your stuff and dump it in a bin, okay? That's the magic bit, okay? And, you know, it's like that, and this kind of thinking has always been there. There's a cartoon from the 1920s of a man listening to the radio, and he's listening to a concert, he falls asleep, and at which point the radio stops, the back opens, and out come these little orchestra people, little elves, and they're going off home because their work is done, they've done their playing, you know. That's not quite how it works. Now, what the system does is that it brings order, and that's why system is here expressed in a very logical kind of shape. And that's the user interface. So that's the bit you work on. So what do you actually do when it comes to user interface design? Well, what you've got to do is that you don't have direct control over the mental model, but you do have direct control over the system. In other words, call it system image, the way it presents itself. So you can try to control the mental model that the user has. And you do that by having, let's say, a graphical user interface based on the Windows metaphor has been shown to be a pretty good way of controlling mental models and allowing users to use a system consistently and error-free. But saying that isn't very helpful, because what we're really talking about is what the user needs to do. We're talking about tasks, because everything is about doing things. So whether you want to do some sums using a spreadsheet, whether you want to write something, okay, using a word processor, or whether you want to do some graphics using a graphics package, okay, these are still tasks. So what user interface designers are doing is that their primary focus is not really on just making things look cool, you know, like look at this slide, it's got some visual design here, which is the university's standard design, okay, that's neither here nor there. The message would still be the same even if there was no eye candy here, okay. So the task here is the all-important part. We need to understand tasks, which is why I started you off last week with hierarchical task analysis, because good HCI is always based on an understanding of tasks, and you will end up doing task analysis one way or another. And so what you have here in the lower diagram on the left is you have computer tasks and you have human tasks, the way we like to do things, and then what the computer can do. And we're trying to actually marry them together so that the computer tasks are supporting the user tasks as naturally as is humanly possible. And the humanly possible is your job, as you as a human designer can make it possible, okay? So we end up, that's the goal is the diagram on the right, known as seamless interaction, totally natural interaction. So do you think that will ever be achieved? No, I don't think so. No, not really, but there are already pretty seamless interactions on certain tasks, okay? Not perhaps all tasks, and some of the results here are quite surprising. So you might think, okay, natural language must be the way. We'll talk to computers just as they do in Star Trek, okay? In the old Star Trek, hello computer, give me this, give me that. Well, this has been studied quite a bit, and it turns out that it's not the best way to interact with computers. Our language is so redundant. You know, when we talk with people, okay, not with computers. So in order for that to be usable, we need to talk like binary. We need to talk in a very kind of clipped, strange way to make it efficient, okay? So, virtual reality, okay? So immersive virtual reality. Well, that's about as seamless as it can get, in the sense that you are inside something, you lift things, you hold things, you touch things, and so on. But is all that necessary for when you want to type a letter to your mother? You know, do you have to actually, in the virtual reality, grab the old typewriter, put it on here, put a piece of paper in it? No, you don't, okay? So it's not very efficient, okay? So there are techniques which allow for fairly seamless interactions, but a lot of them actually don't require it. So you end up trying to find ways which are most efficient, given the resources you've got in the machine and so on, and then was the directive. This EC directive was, okay, efficient, given the resources you've got in the machine and so on, and then, you know, testing it with the users. Okay. This is the EC Directive 9270 EEC, okay? And it defines usability as being effectiveness, learnability, flexibility, and attitude. This EC Directive was adopted as part of law in this country in 1992, I think it was. The directive came out in 1990, and is actually enforced through insurance companies, which is kind of interesting because it is part of being fit for purpose. And if you're going to get insurance, the insurance company will make absolutely certain that you are following all the rules, and that includes having effective, learnable, flexible, and having the right attitude from the users. Which, how do you get there, by the way? By evaluating them, by collecting data, okay? So this law, when it came in, it was oriented towards health and safety and specified standards for hardware and furniture, but also specified how software should be made more usable. It was slipped in kind of as part of it, and it was quite clever. So we don't end up with having a sort of, usability police force that goes around checking whether you're complying with usability laws. I found it very disappointing. I wanted to be a usability stormtrooper, kicking down doors and checking people's software, but sadly that was denied me. So we go back to something I showed you last week, which is we have the basic user-centered model, okay, which is we have perception, memory, thinking, motor skills. We actually have requirements that we study. We do some kind of user-centered design, we prototype, we evaluate, and the iteration goes back to the requirements. And in real life, it is actually done through the Harts and Hickson type model, which is it all happens in parallel with the evaluation as the controller, because that produces the data which says this is working, that needs improvement, this is ready, okay, do that again, etc., etc., etc. It's all based upon data of some kind, okay? Now, the need for systematically collecting that kind of evidence links then also to the fitness for purpose, because the insurance companies want you to keep that data, because if you get sued by someone who is a client saying the system you produced for me is not fit for purpose, the insurers want to look at the data and say to the people, you are not correct, this was done with your users, you've just changed your mind as to how it should be, okay? Which, by the way, is the reason why government projects tend to overrun and cost 3 or 4 times what they were originally thought to cost, take about 4 times longer. It's been studied, and it shows that it is actually the client, i.e. the government, mostly the Department of Defense in America and Ministry of Defense here, changing the goalposts and changing their minds. Now, the core to all this is evaluation, okay? And evaluation involves a bunch of methods that can provide an overall measure for US experience of a certain activity or a system. Fine. But evaluation is also a dominant activity. It guides the rest, it tells you when you're ready, it tells you how well you've done. And it is all about how to measure, what to measure, when to measure, and what to do with those measures. And this is, by the way, if any of you have an interest in working in the area of UX, it's evaluation skills that get you employed as a UX developer. Because the industry is desperate for people who've had some experience of doing evaluation, and you will get that as part of this module. And not to mention, if you are up for a job like that, I will write you a reference and lie a lot. Okay? No. But it, of course, begs the question, how good or reliable are the measurements that you're taking? Hello? Everybody stare at him, go on, stare at him, that's it. Make him feel self-conscious. Good. So, what you have here is the bell curve, okay? And most of you will not have heard of Incas or midges, but you came through school being judged. If you came through school in Scotland, you came through being judged on midges and Inca scores, okay, which are normally distributed. Now, there's a human characteristic, which is that almost all discrete data, human data, ends up looking like this, okay? It ends up as a bell curve. Most famously, we talk about IQ. And IQ has an average of 100, okay, plus minus 15. And that's the real point I want to make, okay? Although staring at the bell curve can be very healthy because it tells you a lot about all kinds of work, including a lot of work in UX. Now, what does this plus minus mean? If we actually measure IQ, and the average IQ is 100, and if you have an IQ of 101, surely it just means you're above average. Or if you have an IQ of 99, you're below average. Not a lot, but just a little bit. Okay? End of story. No, it's not. Because what we're talking about here is the question, how reliable are the measures? And there's something called standard error, okay? Also known as standard deviation. And that is an estimate of how accurate any measure is that you take, okay? And I will teach you about those. So, across the entire world, IQ has been shown to have an average of 100 plus minus 15. So what does that really mean? It means that any other tests cannot measure accurately beyond being somewhere between 85 and 115. So is 85 and 115 the same score? Yes, it is. And both are the same as 100. Okay? So any score that lies between 85 and 115 is average. End of story. Okay? So, in your honours project, you have developed a new little interface and you want to see if it gives a better result in terms of fewer errors than a previous interface that you're playing with. Okay? Now, on average, in the old one, people were making 100 errors per 500 click tests. In yours, it's only 20 on average. Is it? So, the average needs to be calculated and seen in terms of the error. So, if you measured it, if we did an IQ test in here, this is going to, we can start and how it's understood. Now, we want to measure user experience, okay? And we can start with a very, very simple, kind of informal measurement, which is bad UX versus great UX. Bad UX, I hate everything and I hate you. Okay, that's a pretty good expression of bad UX. And great UX, I love my life, I love you, and I love puppies and kittens and flowers and everything. Okay? So these would be two measures, two expressions of good and bad. Okay? Is it useful? Probably. You know, but we would like to have it a bit more subtle, right? Something we can actually quantify, that we can understand, but this is qualitative and it also contributes. So, what this tells us immediately would be that we have very differing UX experiences here, ranging from very bad to great. Okay, so one of the things I'll show you probably next week is how you can have scaling, which does looks at UX and usability separately. So you can actually have a bad UX experience with a highly usable system and vice versa. Okay? But before we proceed any further, you need to understand what is proof. Okay? And this is something which is absolutely fundamental to your thinking. It's about scientific proof and the scientific method. And I'm not going to finish it all today. I know this is heavy stuff, so we'll spread it across today and next week as well. Okay? And I'm going to address that. I'm going to address also the problem of hypotheses, which is particular you know, there's a general issue of how you formulate hypotheses and how that works. But there's also a very specific issue to do with UX and how you actually solve that. And then I want to also talk about presenting scientific results, because, you know, probabilistic proof versus formats, parameters, how it's actually done. So let me warn you immediately that if any of you put in an assignment, I have just proven, right, I will put your assignment in the shredder, because there is no such thing as absolutely proven. So, throughout humanity, we have many different ways of what we consider to be proofing, okay? So, early humanity relied on one-on-one mapping as proof. We see it and we interpret it, okay? This is just based on experience. And this means that, of course, we all know that the Earth is flat. You tell me that the Earth is not flat. Give me an experience which shows that while I'm walking around this place, the Earth is not flat. You can't. Now, I've been walking around for a long time and I've never fallen off the edge. So, Earth must be flat. Okay? So that's one-on-one mapping. I don't have access to a high-altitude balloon which takes me up and I go, oh shit, it's circular, you know. And neither have I been through the experience of, for example, the Vikings, who sailed in one direction and never fell off any edge, but found America and decided it was boring, and so they moved on to the Middle East. Can't resist that one. Okay? So in other words, one-on-one mapping is an agreed view. We as a tribe agree that the Earth is flat because we have no other experience ourselves, is what we see, okay? And we have a tribe, we are the elders, that's it, end of story. Now we still do this today, okay? We are reluctant to sometimes give up some views which we have, and I'm not going to try to think of an example, but you know, you find yourself kind of resisting things because it goes against your day-to-day experience, so you have to actually think a bit more and accept something, okay? But our generations are getting very much used to this, because with science and technology, okay, our views of the world have changed dramatically, okay? And we're expected to cope with that almost on a daily basis. There's always been dogma, okay? A dogma is a form of proof which comes from a higher authority. And the higher authority is usually through God, religious texts of some kinds. And there's a whole area of study, hermeneutics, which is the study of texts, and it is used in anthropology and so on. But essentially, there are people who are appointed as interpreters of texts, some kind of religious text, and they speak on behalf of the authority that lies behind that text, okay? Which means that proof is an order, okay? An order saying that I have decided that this is what's going on, that is dogma, and the text is what's called canon, and therefore you must obey. If you don't obey, okay, then you are guilty of heresy of some kind, and you'll be punished, okay? Thinking, okay? Interpreting evidence in the context and proof. It's still an accepted way of proving things to people. We have an interesting sort of sideline to that, which is legal proof, okay? Because legal proof is a form of interpretation, okay? Now, in law, we have judges, okay? And judges are appointed leaders, so they're almost like religious leaders, but they actually have a job of interpreting evidence in the context of written law, the canon, okay? Now, what's interesting about it is that, you know, it's part of some kind of, I suppose, sociology, anthropology, that we have a system whereby we have to come to a conclusion about guilt or responsibility, and there are many different ways of doing that. But one of them, for example, is to have a jury system, and a jury system could be our peers, like in this country, or it could be a panel of judges, or even a panel of elders, etc., etc. But they actually use a balance of probability, okay? So in our legal system, human judgment is used, but the way it's done is rather interesting, because from a kind of viewpoint of how humans think. Because what you must do is prove beyond reasonable doubt, okay? Now, if any of you are Star Trek fans, then you will realize that the Cardassian Empire has the opposite. You are guilty. For example, the judge will, they've been toing and froing and having doubts, which it doesn't mean. You have here is human reasoning and judgment with some guidance. And then we have maths. Now, the only people who can actually talk about proof is maths, okay? But it doesn't mean necessarily what you think it means, okay? So, to summarize that a bit brutally, there is a mathematical proof which shows that time can go backwards, okay? And when that was implemented in a software model, it actually executed perfectly. And as the mathematician who was doing it said, here I sit, time goes backwards, but I am not getting any younger, right? Because mathematical proof is not the same as empirical proof. And what we're interested in is empirical proof. In the same way that some years ago, there's a mathematical proof known as the Bernoulli effect, and this is the mathematical proof that shows that the air pressure underneath a wing, or can be used for that purpose, underneath a wing of an aircraft, actually makes the aircraft lift and fly, okay? Now, some smartass showed that there was a fault in the proof. It didn't work. And you know, not a single airplane fell out of the sky. Okay? And the proof was then corrected. Okay? Because the idea is sound. It was just a technical thing to do with the maths. Okay? But maths is very important to us because it is the basis of how we do the other scientific thing. And I know very few people that I would call proper scientists, and Jean-Claude is one of them. He is good. He is good. Goodbye. So, maths is a sequence of statements, each of which is either validly derived from those preceding it, or it is an axiom or assumption to follow with gravity. So they couldn't observe shit. That's the moral of the story. Had the empirical test taken place when it was supposed to, his reputation would have gone down the toilet. Okay? So we owe a lot to that one little rain cloud. So this is where I want to stop then. And so we'll carry on next week, because this is now something you need to really come to terms with. And as you will see as we go on, is that the two kinds of data gathering methods, one being formative during the process of design, the other one summative, which can be done at any time but is fairly quantitative, are part of evidence-based practice. They are part of collecting evidence which must be available to any designer, and they guide your design. They tell you what to do. So the message I was getting across to you, or trying to get across, is that only mathematics proves things. Okay? They're the only people who can have proof. Oh. Well, it's just my voice anyway. I haven't moved on. Thank you. I know I should have stayed in bed. Mathematical proofs and science. You see, mathematical proofs underlies science. Who knows? The scientific method thing, we do it by rejection as well. Now, from these lectures, from these slides, if there is one thing, just one thing that you take away, which is a basic understanding of the scientific method as depicted in this diagram, then you've achieved something really good, okay? Because, believe it or not, this actually sums it all up. And this diagram, or these two diagrams, they form a pair of diagrams, is associated with a philosopher of science called Karl Popper. And he, in the 1930s, wrote on the methodological basis of all sciences and showed logically with proof, mathematical proof, how hypothesis testing works. In other words, it was he who showed unequivocally that you cannot ever prove anything beyond anything else. Okay? So what you do is that you have to apply the probabilistic methods of saying it is most likely to be this. Okay? Now, that doesn't mean that science was invented in the 1930s. Science had been going on ever since humans actually tried to invent anything. But what he did was to formalize it. Okay? He produced the actual foundation which can be read as books. So his book on the logic of scientific discovery, produced originally in the 1930s, and is still in print. You can still go get it. You can get it off the web even, and it's very beautiful. So basically, what Popper did was to show that there are two ways in which the scientific method works. One is known as the hypothetico-deductive method. Hypothetical is just Latin for to deduce hypothetically. Okay? And what characterizes this is to formulate testable hypotheses, okay, and then to collect evidence whether that hypothesis works in the most rigorous way possible, and hence the reference to rigorous experimental control. Something about that. Well, you don't stop and say, road not familiar, cannot cross. Okay, and maybe right. And the diagram basically feed back into the theory, either by saying, nah, that doesn't work, yes, that does work, we accept, we reject, or whatever. Okay? And so once you've done that, you're not done, it just comes the next one. Now the strongest kind of example of this is physics. Okay? So there are all kinds of simple hypotheses in physics, and there are complex hypotheses in physics. Okay? Fine. I'll come back to that in a moment. But there's also another method, which is called the hypothetical inductive method. Now, induction means to go, okay, from specifics to general. So it's the opposite of deduction. Now, those of you with any interest in artificial intelligence work, expert systems, smart systems, whatever they're labeled these days, you know, because basically AI is AI and it's been going on for a very, very long time, okay? However, it's to general theory, become deductive, which is basically molecular biology and genetics, able to out in their good experiment and find work and on a test actions. By asking, you can do it by various ratings, etc., etc., and it really, really is important. Okay, so learn about the differences between deductive and inductive, and you're well on your way to becoming good evaluators. So, these are the processes of science, okay? Induction, forming the hypothesis from general observations. Deductions, making very specific predictions based on the hypotheses. Observation, in a very generic way, collecting data that tests the hypotheses, and then verification, which is testing against further observations. And of course, when you've done a study, you've done an experiment, you don't say, well, I've now shown this. Well, bugger me, I'm going home now. You know, I'm done. No, it's not. It goes on and on and on and on. Okay? Which is why, for example, in your honours projects, you're being asked to do literature reviews, because it shows you what has worked and what is working, what is reliable, what is not. Because you can have a good set of results, and you're the only one who's ever seen them. You can even replicate your own experiment and find you don't get it again, so there's some other reason for it. So the sort of boring side to describe is that good science repeats itself by the same people and others over and over and over again. Okay? So sometimes you do it with real people, sometimes you do it with simulation. Given that Jean-Claude was here earlier, you all know Jean-Claude, when he was doing his PhD with me, he was building a system to simulate users. And we used to run experiments with 100,000 replications for each user and 100,000 users. Okay? Because we could simulate. So that's when you begin to say, I think this is reliable. Now, here comes the hypothesis bit, okay? It is done by rejection, okay? Now, what you are really interested in is what's called the positive hypothesis. That's your interest. Direct, okay. Hypothesis. A medic knew about the Popperian methods and the science methods and was using them to describe Sherlock Holmes. Now, you always start with a problem, okay? And the problem becomes a question, and the question becomes a statement. So, take for example here, positive hypothesis, objects will fall to the ground due to gravity, okay? That's a testable hypothesis, is it not? Objects will, the alternative is that objects will rise up or they will hover. Somebody like to drop their pencil? We know it's going to hit the floor. Yeah, exactly. Well, that's a form of hypothesis testing. I have this dream that one day I can do this and say to students, now watch this, and it just stays there. You know, hey. Now, this is indeed a testable hypothesis. So, interestingly, there are something called the simple sciences. And simple sciences are physics and chemistry and the like. And they're called simple because it's easier to formulate hypotheses. Whereas complex sciences are psychology, biology, medicine, HCI, and so on, okay? Because it's harder to formulate the hypotheses. But you have a theory in saying, because a hypothesis must test a theory, okay? Now, comparing two things and saying, well, A is bigger than B, you know, that's my hypothesis, isn't really acceptable, because you need to have a theory that says why it should be, okay? This doesn't stop you from doing it, okay? But you are not testing a proper hypothesis. So, they must be linked to theory and they must be testable, okay? Testable means a meaningful null hypothesis that can be tested. So, for example, Stephen Hawking, the physicist, the very famous physicist, said in an interview, "Do you think you'll ever get the Nobel Prize?" And he says, "No, I won't." Because the Nobel Prize says that for a theory to be awarded a Nobel Prize, it must have been tested. And there's no way that anybody can think of actually testing a black hole theory. Okay? So, no, there's no attestable way of doing this. Some of Einstein's work, for example, on gravity waves, were formulated in the 20s and 30s, and it's only in the last year that a particular experiment has shown the existence of a gravity wave. Okay? So he was right. 6 math hypothesis. I can't easily formulate a hypothesis. That's okay. You can still do the study, because what you do is that you do an inductive approach. Okay? And what you do is that instead of having a hypothesis, you actually carry out a set of observations and you explain them inductively. Now, it doesn't deeply and profoundly affect what you do, you know, what I've just said, but what actually happens is that your way of thinking changes. But what does not change is that you are rigorous. Now, the word experiment, people use it quite loosely to mean I'll try something out. So if you said, well, I can't load my profile, I'll try that. Okay, I'll experiment with it in the afternoon, kind of thing. And then it just means to try something out. Fine, you know. But that's not correct, because the word experiment actually belongs to statistics. Okay, it has a very specific meaning, which is a statistical design to conduct hypothesis testing in a certain manner. Okay, and it's quite strict. So some people might say that only hypothetical deductive counts as experimental because it has hypotheses, but that is not correct, because inductive also has the same rigor as experiments. So if you apply that an experiment doesn't necessarily just test a hypothesis, it is characterized by its method, by the strict way in which things are carried out, then experiments are a statistical term used for both inductive and deductive reasoning. Okay? Now, what's an experimental design? Duh. Well, an experimental design relates to how you collect the data, okay, and what you then do with it. So, in a properly designed experiment, you actually decide beforehand exactly what it is that you're doing, how you're going to do it, even the analysis that you're going to do in terms of the statistics. Everything is rigorously planned as part of the experimental design. So, the key here to the design itself are the variables. You've got three kinds of variables. One is called the independent variable. The main other one's called dependent variable. And then you've got things like confounding variables, which I might do something on later. That's kind of things that ruin your day. Okay? But an independent variable is something which the experimenter plays with, varies, does things with, independently of anything else. So, let's go back to the simple example I mentioned earlier. You're interested to know whether your new interface A is in some way better than your previous interface B. Okay? then your independent variable in your experiment would be interface. Okay? And it will be described as having two levels. The levels are type A and type B, the two different types of interfaces. Now, what's a dependent variable? Well, the dependent variable depends on the independent variable. It is what you measure. So, let's say you decide to measure number of errors made, the speed at which users react to things in your interfaces, and let's say some measure of user satisfaction. Those would be your dependent measures, okay? And they depend, hopefully, on differences being there because it's either interface A or interface B, okay? Tasks that they're doing, and you change the lighting for some of them, their performance will change ever so slightly. However, the results are probabilistic, always probabilistic, and it's a straightforward what's called population probability or total population probability if P then Q under certain conditions R, S or T. Okay? If there are any smart asses in here who are going to stick their hand up and go, what about Bayesian, which is a different way of doing things, you bet. Bayesian has a major contribution to make to actual experimental analysis in this day and age. Okay, it's a refinement on the original probabilities. One thing you'll notice is that the word causality and cause is rarely mentioned. Okay, because it's almost impossible to actually say that something caused something else. Might actually, and it's looking for less than 1% or more, lower, I mean, in terms of probability of falsity from dissertations. And here we got something which, for example, you've got absolute versus comparative experiments. So a comparative is old system versus new system. This could be interface A, interface B, okay? And so a factorial diagram shows that we've got old system and new system and two different tasks. So, what about the variables I was mentioning? Well, this study has two independent variables. One is type of system, old and new, and type of task, 1 and 2. Okay? The dependent variables here could be things like time, errors, user satisfaction, number of clicks, etc., etc., etc. Okay? But there are also an important difference between this type of study, which is one system compared to another, to a different kind, which is absolute, and that is comparing your system to a published metric. And that happens quite a lot in UX work. So it means that there's been some studies done. It's known that you should be able to get to any information within about 6 clicks. Okay, so you compare your system with that. Okay, so same game though, which is that you are comparing your results with those of a previous published something or other. Okay, and the kind of information here is that you've got descriptions of things, you've got ratings of things, you've got protocols, which means talking out loud, questionnaires. There's endless possibilities for collecting data. What you'll find that it's a lot easier to learn how to do that than you think, because you tend to go with what others have been using because it's tried and tested already, and mistakes that other people have made, the mistakes that you might make have made them for you. Okay, so you can learn from it. Okay, so what about presenting results? Well, like I say, all results are based on probabilities, and the first thing you must do is to present the characteristics of the data that you've collected. Okay, and you must look at how reliable it is. The most bog standard approach is to use what's called a measure of central tendency. This is before you do any testing. And there are three methods of central tendency: arithmetic mean, also known as the average. There is the median, which is if you rank your scores, the one in the middle, okay, and the mode, which is the most common value. Now, in UX, median and modes tend to be used on occasion because you've got limited what's called ordinal data, lots of ones and twos and threes and three scores for people rating themselves. Again, we'll come back to that, and I'll show you how that works. However, they're all basically measures of central tendency, and you often tend not to use just one but others. But if you've got data which is like time, then mean is always the best. If you've got a scale 1 to 5 or 1 to 10, then median and mode might be more appropriate. That kind of decision making we'll come back to. However, the big point I want to make is go back to the bell curve and IQ 100 plus minus 15. Okay, this is the standard deviation, and this is the all-important measure that I want you to work with, and we will work with. What it means is that the low standard deviation indicates that the data points tend to be close to the mean. Okay, high standard deviation indicates the data points are spread out over a wider range of values. So obviously, the lower the standard deviation, the more reliable your measurements. So IQ of 15 is very, very stable and has been for over a century. That's the best you can do. Okay, so if you find you've done a test of IQ and your standard deviation is 50, there's something wrong with your test. Okay, it's not measuring things reliably. Okay, but what it also means that you need to understand is that it means that average IQ is between 85 and 115, and that all the scores between 85 and 115 are statistically the same. Okay, or treated as equally. So what you're looking for is low standard deviations. What does high standard deviation mean? It means that there's something wrong with your experiment. Your data is not controlled well. There's something up with it. And I'll show you examples later of how how easy it is to actually make a mistake and get your variance up or standard deviation up, and how stable some data can be. Okay? Break time.